Hi everyone, my name is Jessica Paquette, and I'm here to tell you about how you can make your code really, really small. Today we're going to talk about four main things. Here's an outline. The first thing is, why does code size matter? The second is, what exactly is outlining and how might we build a prototypical outliner? The third is, how well can we do using this sort of method? And the fourth is, what's in the future for outlining? All right, so let's start with a motivating example. Let's say that you're working on a program for some sort of embedded system. You've got a tiny computer and it's got a few kilobytes of memory. One day, you notice that your program is bordering on filling up all of the available memory for your device. Hoping for the best, you keep writing code, but one day, to your dismay, you find that your program no longer fits on your computer. So you scratch your head a bit. You notice that at the assembly level, your program contains lots of these identical sequences of instructions. So you find each sequence of instructions that appears at least twice. And what you start doing is you start copying and pasting these sequences out into their own functions. You then replace each instance of these sequences with a call to the new function. After doing this, you happily find that your program is now small enough to fit on the computer and you can sleep easily at night. This process is what we would call function outlining, or just outlining for short. It's a code size reduction technique which works by finding repeated sequences of instructions and pulling them out into function calls. So let's say that you want to automate this process. You might want to build something that we might call a function outliner, or just outliner for short. This would be something that sits inside the compiler and finds these sequences for you and then automatically outlines them. So you sit there and you scratch your head, and eventually you notice another thing about your problem. So you want to find repeated sequences of instructions in your program. Well, this is similar to the problem of finding repeated substrings of a larger string. So you write down each instruction as a letter. Two instructions get the same letter if and only if they do the same thing. So that leads you to your first major observation. Programs are like strings of instructions. So now your goal is to find repeated substrings in your program, which you would then pull out into functions. So with this in mind, you probably want a data structure that will allow you to do this efficiently. For the purposes of our outlining prototype, we used a suffix tree. A suffix tree is a type of search tree on strings. The leaves of the tree represent the suffixes of some string, hence the name. Note that this is not a certain related structure, which also, unfortunately, is pronounced suffix tree, or suffix try if you dislike ambiguity. Suffix trees are an extension of that structure. Effectively, they're compressed suffix tries. Now, for those of you that don't know what I'm talking about, don't worry. Here's an example suffix tree for a simple string. Say ABC, AB, and then a unique terminator character. The nodes in this tree represent substrings of ABC, or ABC, AB, and then the terminator. For example, the root is the empty string. The two internal nodes, A and B, represent the substrings A and B respectively. The top leaf off of the B node represents the suffix BC, AB, and then the terminator. In each node, we're going to store the start and end indices of its respective substring. If it's a leaf, we're also going to store the index that suffix corresponding to that leaf starts at. The arcs in the tree are labeled with substrings of our actual string. These represent valid transitions between two given strings in the tree. From any node, there's going to be at most one arc leaving it that starts with some given character. So what can we do with this thing? Let's say we wanted to find the longest repeated substring of the string we've stored in our tree. Well, notice that a substring only appears more than once if it appears in more than one suffix. So if a substring is a suffix, then it has to be unique in the main string. So therefore, the only candidates are the internal nodes of the tree. Now, we know that the empty string has length 0, so the root is out. But what about the other two nodes? What we can do is we can look at the strings that those nodes represent and choose the longer of the two. In general, what we're going to do is we're going to traverse the entire tree and find the internal node with the longest associated string. Now, what if we wanted to find all of the occurrences of the longest repeated substring? Well, we know the length of the repeated substring. We also know the length of the strings associated with its leaf children. We also know the start index of the suffix stored in each leaf, so this is enough to tell us exactly where each repeated instance occurs. So, suffix trees were a good choice for our prototype for three main reasons. First off, you can construct them in linear time. The prototype implementation uses Yukonen's algorithm for suffix tree construction, but there are many other linear time algorithms. Second off, we can find the longest repeated substring in linear time using the method I just described. Third off, we can find the most frequent substring of a minimum length in linear time as well. This is kind of cool because we could come up with other cost models for outlining. For example, maybe there is a short substring that appears a lot, and it would be better to outline than a long substring that appears, say, 2 times. All right, so now that I've told you about these things, how do we build them? I mentioned that I used Yukonen's algorithm, but for this explanation, we're going to use a simplified algorithm that'll give you the gist of things. Okay, so on the left, we have our string and the suffixes that we need to add to the tree. What we're going to do is we're going to build the tree iteratively, with each tree building on the previous one. Okay, the first tree that we're going to build is the tree that's just for the empty string. This is just the root. There's nothing to add at this step, so we're just going to look at the next tree. Okay, so what we're going to do now is we're going to look at each prefix of our string, and we're going to add all the suffixes for that prefix. Our first prefix is just the string consisting of the character A. Now, this has just one suffix, and the first thing we notice is there's no edge leaving the root whose label starts with the character A. So we can just throw this in the tree as a leaf. Okay, we have nothing left to add, so we're going to move to the next prefix. All right, so now we have 2 suffixes to add. Well, notice that we want to add, say, AB, but we already have A in the tree. Well, that's the same as just tacking on B to the end. So if we kept, say, an integer or something, some index into the string that would tell us where the leaf is at the end at, we can just do this in one step. Now all we have to do is add B, which we can do in the same way that we did before. And that's it. All right, so now we can move on to the next prefix. We can extend that leaf end, and then all we have to do is add C in the exact same way. All right, that's pretty straightforward. So let's move to the next one. Okay, so we've extended the leaves, and now we have to add the suffix A. Well, that's problematic because we already have an edge leaving the root whose first character on its label is A. So we can't just add this as a suffix. So what we're going to do instead is we're going to remember where we found it. After that, we're not going to add anything. We're going to move to the next prefix. What we're going to do is we're just going to extend these leaves, including the suffix that we just missed, and we're going to look at our next one, ABCAB. Now we have 2 things to add. Right now we're looking at the character B. If we try to add the one that we missed in the last step again, what we're going to notice is that this actually matches the next character. So we can't add this one either. Now, there's also another node that corresponds to the next suffix B. So we can't do anything there. So we're just going to extend the leaves, pay attention to where we found this, and move on to the last prefix. Okay, so the next character is the terminator. Well, the terminator is unique, so it doesn't match with anything in the string. So we have a mismatch on our saved edge with the suffix that we want to add. So what this means is from the point that we matched up to, that is up to AB, there are two ways to reach a suffix. To represent this, we're going to split the edge. That is, we're going to create a new internal node whose incoming edge is labeled with AB. We'll chop AB off our old leaf and make it a child of the new node. We'll also add a new leaf for the terminator. This lets us choose either of the suffixes by moving from AB. Now let's try to add the next thing. Well, the first character B matches an edge, but the second one doesn't. So what we're going to do is we're going to split this edge as well. Now all that's left is to add the suffix for the terminator. Well, there's no edge leaving the root that starts with the terminator, so we'll just add a leaf for it. And now we have the full suffix tree. Now, note that the actual construction algorithm is more complicated than this. We reach linear time construction by taking advantage of a few tricks. One of these tricks, for example, is that we have a path between certain internal nodes, which allows us to avoid repeatedly querying the tree during the split step. This example also didn't cover the case where we, say, have internal nodes that have non-leaf children. These extensions are tricky and outside the scope of this presentation, but they're very natural extensions. So let's talk about how you might represent one of these things. Roughly from a simplified standpoint, we might have something that looks kind of like this for our suffix tree. We'd have a pointer to, say, a root node, we would keep track of the leaf end, and we would keep track of some information for our splitting operation. For example, we might want to start our query later down in the tree. Now, we're going to add a few functions for the outliner. We're going to have a function that'll give us that longest repeated substring that'll be our candidate. We're going to have a function for finding the occurrences of some query string if it appears in the tree. And we're going to have a pruning function that will allow us to reduce the search space by marking out nodes associated with some string. Our nodes might look something like this. We'd have a pointer to the parent of our current node that would allow us to split things. Each node might store something like a map of whatever we want to store as characters. It could be unsigned integers, for example, to nodes to represent whether or not there's going to be a valid transition on that character. Each node is going to store those indices into the string that would tell us what the substring is associated with this thing. And each leaf would also have that suffix index. That's the start index of the suffix it represents. For the outliner, we'll also add something like a Boolean value, which will represent whether or not a node has been pruned out of the tree. So now that we have the main data structure for the outliner, we can move on to a simple example. Let's say we have some sort of toy program that looks like this. We don't really care what it does, we just care about the outlining part. The first step is to encode the program as a string. Let's say we've assigned labels or characters to the entire program, and we're going to write out each basic block as a string. I'm going to explain why we do basic blocks a bit later, but for now, just hang tight. So next, we're going to append one of those unique terminator characters to each of these strings. Finally, we'll just concatenate them together. Now we have a string that represents the entire program. So those unique terminator characters, these are interesting. What's going to happen when we put this in the suffix tree? Well, what's going to happen is it's going to make sure that all of our candidates are fully contained inside one basic block. This is because the terminator for each of these strings is unique, so they can be included in no repeated substring. I still haven't explained why we want the basic blocks, but we're going to get to that eventually. The next step is to put everything in the suffix tree and find our outlining candidates. So here's the suffix tree for that string. Please just trust me that this is the suffix tree for that string. We want to find those long repeated substrings in the program, so we're going to do the longest repeated substring query I talked about earlier. We're going to walk the tree and find the internal node that has the longest related string. So we'll just do that. Just walk along the tree. And okay. So now we've determined that the longest repeated substring of this program is, in fact, ABC. Now we need to do two things. First off, we need to make sure that we find ABC only in this phase of outlining. Second off, we need to find where it actually appears in the program. So we're going to query the tree for ABC. Now, each internal node that we visit along the query must be associated with it. So in the future, we can never visit those nodes again. In this case, it's just this one node. So we're going to mark it as invalid. But we're not done. In this string, every instance of C and BC is contained in an instance of ABC. So we have to invalidate those nodes as well. So we'll just say that we'll prune them out of the tree. This is going to prevent us from trying to outline certain types of overlapping cases. Just so you know, you don't have to find these instances manually. The full construction algorithm gives us a way to do this quickly. All right, so now we just need to find out where ABC occurs in the program and outline it. Now remember that the leaves of the tree store all the information that we need to find our candidates. So we're going to visit each leaf. And after doing this, we have every instance. So normally we would continue this process until we hit either some sort of stop condition or we run out of potential outlining candidates. However, in this case, I know that the only candidate is going to be ABC, so we'll just go straight to the outlining part. Okay, so let's start outlining. The actual outlining process is in two parts. The first part is we just create a new function and insert it into the program. The second part is to remove all instances of ABC, for example, and replace them with calls to the new function. To do this, we're going to look at each occurrence of the string and each occurrence in the program at the same time. In the program, we'll replace the instance of ABC with a call to the new function. In the string, we're going to represent that call as a new unused character. So we'll just outline the other two occurrences. And that's it. We've successfully outlined ABC and we've reduced the size of our program as expected. So now that we understand the algorithm, we should talk about some limitations that came up when we were building the prototype. The first limitation is not everything is immediately safe to outline. Consider this program. You don't really have to try and parse it, but what I do want you to notice is that there's a conditional branch in it. Now let's say that the outliner found this sequence for whatever reason and decided to pull it out. So then we might have something that looks sort of like this. Well, this isn't going to work. We would call the outline function. Then if we failed the conditional, we would jump back to print result. Now, the call instruction in, say, x86-64 pushes the current value of the instruction pointer onto the stack. So when you jump to print result, your stack's not aligned to 16 bytes anymore, so calling printf is not going to be good. So this is something that can be fixed, but for the purposes of the prototype, we just stuck to making sure that things lie inside basic block boundaries. Another thing is memory overhead. We haven't seen really any problems with the suffix tree for memory overhead, but this could pose a problem later down the line. So some possible solutions to this are to, say, explore the use of other data structures such as suffix arrays. Suffix arrays have been successfully employed on very large data sets, so it might be worth exploring using them if memory proves to be an issue. Another approach may be to perform outlining on, say, subsets of large programs before performing, say, the full interprocedural pass. Finally, another approach might be to look at the equivalences between higher level structures, such as basic blocks first, and then guiding what should be outlined based off of the result of that query. So, for example, if we know that there is a basic block that has nothing in common with the rest of the program, then we ought not to even consider it in our outlining set in the first place. So, now that we've laid out the algorithm and we know some of the limitations of the prototype, we can talk about some preliminary results. To test the outliner, I ran a vanilla Clang with OZ against the same Clang augmented with outlining on the LLVM test suite, specifically the tests in single source, multi-source, and externals. The outlining prototype was as conservative as possible, so if anything that could pose a problem came up, we didn't even try to pull it out. Now, some programs did really, really well with the outliner, like up to a 40% reduction, and others did really, really badly with no reduction at all. I expect that we can extend these results to about a 20% reduction by being less pessimistic, but it's worth looking at where some of these programs did really well and where some of them did really badly. So the programs that did really well tended to exhibit things like heavy macro usage. It turns out that in the test suite, there are programs that consist of solely macro expansions. There were programs that had lots of manually unrolled loops. And there were programs with, say, heavy template usage. If you have a lot of templated functions and you use them with lots of different types and those functions are long, it becomes more and more likely that you're going to have these repeated sequences, which would be worth pulling out. There was also a lot of, say, automatically generated code. If your code is being generated by some sort of algorithm and it's generating a very large program, that seems like it's a likely source of similarity. Now, there were programs that featured no reduction. Many of these programs were very small unit tests, say around 20 or 30 lines of C. There were programs where we hit those unoutlinable cases, such as those conditional branches, and there were programs where we just didn't win out in terms of register allocation. For example, we could have a sequence of instructions which does the exact same thing in all cases, but it doesn't use the same registers. Therefore, the outliner can't do anything. So, with that in mind, we should probably talk about what's in the future for outlining. The first thing is performance impact. Believe it or not, this doesn't always make programs slower. Some programs would speed up, sometimes significantly. One reason for this is, for example, better instruction cache usage. We can probably mitigate performance hits on other programs by paying attention to whether or not a block of code is hot or cold. Second, actually putting this stuff on a platform that's typically used in embedded systems is a main goal. Third, we could do, say, IR level or pre-register allocation outlining. This would allow us to avoid the unfortunate register allocation issue, and also if we could move the algorithm around in the pass pipeline, we might be able to get some more interesting results. Finally, this is kind of out there, but I'm really interested in using, say, string algorithms for code analyses. Like the suffix tree, for example, could be run on a large code base, which could then find perhaps sources of copied and pasted code, that sort of thing. So, in summary, we had some pretty good preliminary results with outlining that we can expect to get better. And the potential problems with outlining can be avoided. Outlining has a lot of potential. There are lots of cases in the current implementation that we don't handle right now, but we can easily extend it to handle. Also, if you're interested in reading about the outliner, you can go look at the RFC on the mailing list. So, thanks to everyone for coming to my talk. I'm really excited about this work, and I hope that I've made you all a little bit more excited about code size and string algorithms. If you have any questions, I'd love to answer them.